Hello, students. We are here to discuss Newton's second law of motion problems. I have some questions here that I'd like to share with you. Okay. All right. Let's start. Question 1 says that Tamika is pushing a 30-kilogram heavy box horizontally on a level floor. Unfortunately, the box does not move. Assume Tamika's push is 150 newtons. Draw and label all significant forces that are acting on the heavy box. We are told to remember that a force is represented by an arrow. The longer the arrow, the larger the force. All right, so usually when we talk about the surface, we usually draw the surface like this. So our surface here. And the heavy box can be represented by a box. So we draw our box like that. And Tamika's push can be represented by, you can put it here, that's your 150 newtons force, or we can put it somewhere here. So let me put it here. Still, we can put it the same thing. So pushing with a force of 150 newtons force. So right here, label 150 newtons. All right, and we are told that the box does not move. So the box does not move. This implies that there has to be a balanced force, or there are balanced forces on the box. So that force could be most likely due to friction. So we have to draw another force pointing this direction, and this force is also 150 newtons. So we know that this force is equal to the pushing force because the box does not move. In other words, the acceleration in the x direction is 0. All right, now we have to be careful to make sure that we answer the question fully. The question also is asking us to draw all significant forces. For sure, there is gravitational force also. So we have to draw force of gravity downward. And how much will that force be? Well, we have to remember the way we calculate gravitational force. Fg is m times g, and m times g, let me see if I can scroll down. Okay. M times g, in this case, gravitational force will be 30 kilograms times, let me think, I need more space. Okay, come here. Fg will be 30 kilograms. That's the mass of the box. Then multiply by g. I'm going to take it as 10. Usually it's 9.8 meters per second squared, but I'm going to use 10, which is a close number, and it's actually, it makes life easier a little bit. So 10 meters per second squared. Right, so this gives me the force gravitational pull of how much? This will be 300 newtons. 300 newtons. All right, so I need to indicate the force of 300 newtons on the force diagram. And as you can see, this force has to be larger than the 150. So what I'm going to do here is to make the pushing force with a smaller arrow. So let me do this. Get this one out. Okay, so make it shorter here, and also this one, I'll make it a little bit shorter. So it has to be, because the longer the arrow, the larger the force, and vice versa. So I'm gonna make it shorter, 150 newtons here, and this one, 150 newtons. Then this one will be like double that, 300 newtons. Okay, and then we have to understand that if I stop here, it means that the net force is not zero in the y direction. So I need to ask myself, what other significant forces acting on the box? For sure, that must be the support force, which we call normal force. So there is also the support force here. And I can tell the size of that by understanding that the box does not move in the vertical direction. So this must be 300 newtons. If I make this a little bit shorter here, trying to perfect this diagram. Okay, kind of like that. So that's the force diagram that we have. So let's see if we have answered the question fully. Well, there is the pushing force that Tamika is pushing, and we understand that the box does not move. That means there has to be a balanced force. And we were able to know that the amount of frictional force is 150 newtons. We are done in the x direction. For the y direction, we know for sure there has to be the force of gravity, and we were able to get the 300 newtons here, which is pulling downward. We got that by multiplying mass and then acceleration due to gravity g. And we know that the net force in the vertical direction has to be 0. And we were able to tell that this force has to be also 300 newtons. So the net force has to be 0. All right, so that's the solution to problem number 1. We have made sure that the longer the arrow, the larger the force. And I think that's enough for now. Okay, so let's move on to the second question. Okay. All right, so here is the second question. Xiao joins Tamika in pushing the heavy box in the same direction as before. This time around, the box is seen to speed up at 2 meters per second squared. If the force of sliding friction between the box and the surface is 240 newtons, determine the total force exerted by Xiao and Tamika on the box. All right, so I'm going to do the same thing. I'll draw the situation. Usually it's a flat surface, so try to draw my flat surface like that. And I usually put these lines to make sure that this represents the ground. Put your box here, draw the box here. And we have to draw the forces. Well, we know already that there was force of gravity, which we said it was 300 newtons, remember? It's the same box, which was 30 kilograms. But the weight or the gravitational force, by the way, gravitational force is, in this case, is the same as the weight of the box. So 300 newtons. And we had the support force, normal force, we had it at 300 newtons. And what else? Well, we have 2 people pushing. We don't know what will be the total force, so we cannot tell right now. But at least we can put an arrow here to show that this is the force we are looking for, and we call it the total force. That's the total force that Tamika and Xiao are exerting on the box. That's the total force, the total pushing force. All right, and now we are told also the force of friction is 240. So I have to indicate that one also here. That's 240 newtons. Okay, looks like I have all the forces in the x direction and all the forces in the y direction or vertical direction. So I can go ahead and find the total force, but also I have to remember that there is an acceleration. I use dotted lines to indicate acceleration, 2 meters per second squared. That's the acceleration of the box. Let's do it correct. So squared here. Okay, so I have my acceleration. I have all the information given. and my job is to find what is the total force that is exerted by Xiao and Tamika. Okay. All right, so let's see. Well, this has to do with Newton's second law of motion, because I see that I have given, I'm told about the mass of the box, 30 kilograms, 30 kilograms. Should I put here 30 kilograms here? Oh, that want to look good there. So we just have to write here that the mass is 30 kilograms. Okay, the mass is 30 kilograms. So we have the mass, we have the acceleration, and therefore we can find the net force. So I'll go down here. Would that be a good idea? I want you to see what I'm doing here. Okay, here. That would be okay here. All right, so we are dealing with net forces in the x direction. So I put this symbol stands for net force, and then forces in the x direction must be equal to mass times acceleration, but in the x direction. This is in Newton's second law equation. And then we can go ahead and say, oh, okay, this is what? This is the 30 kilograms. And the acceleration is 2 meters per second squared. Sorry, there, okay. And then I go down here to find my net force. So the net force in the x direction has to be, that's 60 newtons. So that is the net force in the x direction. But I can also write the net force in terms of the variables. So look here, we can write the net force in terms of the variables. So this is actually equal to, equal to the total force is acting to the right, so it has a positive sign. So F total, have to add the frictional force, the 240 newtons, this one. So that one is acting to the left. So put a negative sign to indicate that it's acting to the left, then 240 newtons. All right, so this is equal to everything here. This equation will help me to find the total amount of force. All right, so let me see. All right, let's go ahead and find this one. So basically, we're saying that 60 newtons will be equal to, you can write this just total force. I drop the positive sign. Plus times negative is negative, and then you have 240 newtons. So our equation looks like that. This equation will help us to find the total force. I will transfer the 240 to the right-hand side. It will be positive. So transfer this to the right-hand side. It will be positive. So that means I end up with 60 newtons plus 240. See the minus sign here changes to plus when you transfer the equal sign. That will be equal to the total force. And basically this is actually 300. So 300 newtons is equal to the total force. Yeah. So what we are saying is that the two, Tamika and Xiao are actually exerting a force of 300 newtons. So the total force here is 300 newtons. Okay. All right. So, okay. The most important thing is to, drawing helps a lot. If you do the drawing and indicate all the variables that have been provided in the problem, then you can actually figure out, how to solve the problem. And we did that, and we were able to notice that this problem actually involves Newton's second law. So drawing and labeling all the quantities that have been provided helps us to deduce that, you know what, This has to do with Newton's second law of motion. And helps us to solve the problem. All right, so let's go ahead. This is question number 3. Question number 3 says drop one brick from some height, it's 10 meters. Then measure the time it takes for the brick to touch the ground. Next, stack 2 bricks and repeat the experiment. Compare the time of fall between the single brick and the 2 bricks. We are told to ignore air resistance in this problem. All right, so this problem has to do with Newton's second law, but also Galileo's experiment. Remember, Galileo dropped 2 objects of different weights, and he discovered that if the 2 objects are dropped from the same height, they touch the ground at nearly the same time. That means that regardless of the mass, the accelerations is the same. Okay, so we can solve this problem in different ways. So we can explain the result in terms of concepts, but also some mathematics. So let's try to think about this conceptually. So I'll try to remind you that both objects here can be said to be in free fall. So both objects are in free fall. That means the only force acting on them is gravitational force. No any other force is acting, because we are told to ignore air resistance. When that is the case, then we can say that the acceleration in the y direction is actually minus 9.8 meters per second squared. Okay, so this doesn't matter, I mean, whether I'm talking about this only or maybe both of them, the acceleration is the same. And we discussed that in our past discussions, that free fall acceleration is the same regardless of the size of the object. All right, so we also understand that the 2 objects are dropped from the same height. That is important to keep in mind. We are dropping from the same height. All right, and also we have to remember that the initial velocity is 0 because we're just dropping. The idea is you drop, so we are dropping these objects, dropping. So if you drop, that means initial velocity is 0. So we write that as v initial, and then we put a y here. This stands for initial velocity. So for both of them, the initial velocity is 0 meters per second because you're dropping from rest. So drop from rest. That's what happens when you drop an object from rest. The initial velocity is 0. With this conclusion, I mean, with all this, we can say that the time of fall will be the same. Okay, dropping from the same height, we started from 0 speed, and we accelerate at the same rate. So we can conclude that the time of fall will be the same. So time of fall will be the same, Okay, because you're starting from the same height, same initial velocity of 0, then you accelerate at the same rate. So this is the key. You pick up with speed at the same rate. Okay. So if you monitor this, if you had a snapshot, you will see that the 2 objects will be going to the ground at the same rate, and they will touch the ground at the same time. Okay, try to explain this. It's how about mathematics? Maybe we can think about this in terms of mathematics. Well, wait, let's try. Maybe mathematically we can explain this. Remember that one of the equations that we came up with is this one. The distance traveled by falling object, change in y, can be given as initial velocity in the y direction times the time, and then plus the wait a minute, plus 1/2, wait a minute, yes, 1/2 a acceleration in the y direction times time squared. Yes, that's the equation. Yeah. So that's the equation that we have seen before. And when the initial velocity is 0, this part goes to 0, then you end up with the distance falling, changing y is equal to 1/2 a y times time squared, acceleration in the y direction. Okay, that's what you end up with. I mean, as you can see here, time is actually something that we can solve for if we know the height and the acceleration. So we can find out the time in the equation here and solve for the time. Right. So this gives us twice times change in y is equal to a y times t squared. So what I'm trying to do here is to multiply both sides by 2, and then this equation becomes 2 times change in y is equal to ay times t squared. And then we can go ahead and say, oh, wait a minute, at this point, this means what? It means that t squared is equal to 2 times change in y, okay, divided by a sub y. All right, and finally, time there can be found by taking the square root of twice change in y over acceleration in the y direction. Well, I mean, it's just rearranging the equation, and then we get this result. That means for a single brick, you have the same distance fallen here. You have the same acceleration, time will be the same. If you take the 2 bricks, use the same formula, time will be the same. Okay, because we already said that the 2 objects are dropped from the same height. That means delta y is the same for both situations. And ay, we know that we already discussed that the acceleration in the y direction is the same whether you have 1 brick or 2 bricks. So whatever you do here, if you were to calculate the time of 4, you will find that the time of 4 will be the same. Okay. All right. Just when you use this equation, remember that ay will be minus g. All right. Ay usually is minus 9.8 or minus g meters per second squared. All right, and then delta y, since you are going downward, the displacement there will be negative. So the negatives cancel out and you end up with time as a positive number there. All right, so I mean, the inside, everything inside here will be positive because delta y will be negative and ay will be negative as well. So negative cancels out. All right, so that's it about this problem. Let's go to problem number 4. Let's say below is a car slowing down at the rate of 3 meters per second squared as it is going to the right on a level surface. Well, I'd like to put my level surface here. Wait a minute. Okay, so that's the level surface. It's not straight enough, but level surface. And okay, so it's slowing down, going to the right. And that's what happens when there is a force acting in the opposite direction to motion, then objects slow down. Yep, so the net force is acting to the left, so our left, and the object is going to the right here. So it is actually slowing down. Okay, it's a problem here. Well, question says we should find the mass of the object given the acceleration, given the net force in the x direction, find the mass of the object, and draw other forces that are acting on the car together with their corresponding magnitudes. All right, so we can go ahead and say there's another force, this one, that acts downward. And this force has to be mg. We don't know how much that will be, so just say mg until we find the mass. And there is also the support force that will be equal to mg. So there's a support force that will be equal to mg because there is no motion in the vertical direction. Acceleration is 0 there, so it has to be Fs must equal to mg. Okay. All right, so these are the forces acting on this one. And we suppose that the force acting to the left is actually basically maybe due to friction, for example. If it's not, then you can say that in your solution, you can say, okay, maybe we cannot solve the problem because maybe friction is not given. If you assume that the 30 newtons is a force coming from somewhere else. But I guess most of you, you do assume that this force would be most likely due to friction, slowing down the box. All right, so I'd like to find the mass of the object quickly. So net force in the x direction must be equal to mass times the acceleration in the x direction. Now here the net force, which is the single force acting on this one, in the x direction, we only have 30 newtons. So you put 30 newtons, but remember we are dealing with a vector here. So you cannot just put 30 newtons, you have to indicate direction. A force acting to the left, you pick a direction of negative. So minus 30 newtons is our net force. And the mass we don't, and then you multiply by acceleration. We are told in the problem. If you see the problem here, the acceleration is 3 meters per second squared, right there. Hope you see it here. So we can pick our acceleration and put it here. So 3 meters per second squared. Okay, now the acceleration, we are told that it's slowing down. So I forgot to emphasize that that has to be minus sign. So it picks a minus sign because you are slowing down. When you slow down, the acceleration in this case is negative. Or remember, Newton's second law also tells us that the direction of the net force is the same as the direction of the acceleration of the object. So the moment we know that the net force is negative, I mean, it has a negative direction, then the acceleration must be negative as well, right? That's why sometimes I write the the second law, I put arrows. Sometimes I put arrows. So let me show you. It's very, very important. Sometimes I put arrows to indicate that these are the same all the time. Okay, so second law tells us that once I know the direction of the net force is the same as the direction of the acceleration, I deduce that direction of the net force is negative here, and therefore the direction of acceleration must also be negative, right? So they are pointing the same direction here, meaning that whatever direction you have for the net force is the same as direction for the acceleration. Okay. All right, there's a different explanation to explain why acceleration is negative, but I think this is enough for now. All right, so we can find our mass by dividing both sides by minus 3 meters per second squared. Divide both sides by minus 3 meters per second squared. So this cancels with that. Negative cancels with negative. So you end up with mass being equal to 10 kilograms. So 10 kilograms is our mass, and that's our solution there. Okay. Almost there. We have one more question. One more question to discuss. Oh, by the way, we have to indicate the other forces. I forgot. So this force, now we know the mass. This force will be 10 kilograms times, I use 10 10 meters per second squared. So basically this is 100 newtons. And of course, this has to be the same 100 newtons because there is no acceleration in the vertical direction. There's no acceleration. So if I know this is 100 newtons, this has also the same magnitude, 100 newtons. So that completes the problem. All right, so this is the last problem here we need to solve. Says Mr. Wolf stands on the floor of an elevator, initially on first floor. The elevator then accelerates upward. While accelerating upward, two forces act on Mr. Wolf, shown below. While there's gravitational pull there, I can see that 600 newtons. And I can see support force. Maybe this is due to the surface of the elevator surface and pushing Mr. Wolf upward. Okay, so Margaret is at rest outside the elevator in the hallway. Well, yeah, Margaret is watching. Maybe it's an elevator where you can see people inside, even when they are going up or down. And Margaret would like to find out the mass of Mr. Wolf and also Mr. Wolf's acceleration. All right, so let's solve the problem. We are going to start by looking at mass. The question is, if I know if I know gravitational force on Mr. Wolf, I can tell the mass. Just remember that the force of gravity is actually called weight in this discussion. Most of the time, gravitational force is also the weight of Mr. Wolf. That's the weight, W, right? So if that is the case, weight is mg, or gravitational force is mg, then I can go ahead and say that this is a 600 newtons. That must be equal to mass of Mr. Wolf times 10 meters per second squared. I'm going to use 10 meters per second squared most of the time because it's convenient for me. Of course, you might find it convenient as well. It's easier to divide or multiply using a 10. All right, so I will need the mass. Obviously here you can go ahead and divide 10 meters per second squared here. Divide 10 meters per second squared here. This and this cancels out. Then quickly, your mass will be 60 newtons. So that's the mass of Mr. Wolf. All right, we are almost there. And then next we need to find the acceleration. Well, looks like this has to do with Newton's second law. Remember, net force is equal to mass times acceleration. And we are dealing with the y direction, or vertical direction. So we're gonna put the subscripts as y here and the y here to make sure that our emphasis is on the y direction. And as usual, these are vectors, so you can put the arrows, but I'm not interested in that. All right, so let's see. Let's rewrite the net force in terms of the variables, in terms of the numbers given. So we have the 1000 acting upward, so it'll be plus 1000 newtons. Okay, plus 1000 newtons. And then add the other force. The other force is the 600 newtons, but it's acting downward. So I put minus 600 newtons. The result will be mass times acceleration. We are told that the mass, I had the mass in newtons. That's not correct here. This should be kilograms, kilograms. Okay, so 60 kilograms and then multiply by acceleration. So we just put a sub y there. That's acceleration in the y direction. The result here is just 1000 minus 600. So that is actually 400 newtons equal to 60 kilograms times what? 60 kilograms times acceleration in the y direction. All right, so you know what to do here. You divide both sides by 60 kilograms to get AY. Um, so basically, the last step is to find your acceleration, will be the 400 newtons, then divide by 60 kilograms. 60 kilograms. That will give you your result. I don't know if I calculated this already. I don't have my calculator with me here, but I think 6.67. 6.67 meters per second squared. It looks like a little bit on the higher end, because for elevator, I don't know, the typical value should be around 4, maybe 3 meters per second. But according to our values in the program, this makes sense. All right, so I'll stop here, guys. I don't know if I can, if I wish I could share this document. Let me see. Okay, anyway, so yep. Okay, I'll try to save this document and probably share it for those who would like to print it out and follow through what I did here. All right, so I'll stop here. If you have any questions, please do not hesitate to reach out to me. Thank you so much for listening. Bye for now.